So I now want to turn to the question of how to formulate our prediction problem precisely. I want to be precise about how we're defining the inputs and outputs of our predictions, and that in turn is going to have consequences for how we join the corpus and the KB, how we construct negative examples for our learning algorithms, and how we handle multi-label classification. So first, what is the input to our prediction problem? In the supervised learning paradigm, the input is a pair of entity mentions in the context of a specific sentence. We're trying to label a sentence, just like we do in part-of-speech tagging or sentiment analysis. But in the distance supervision paradigm, we'll do things differently. The input will be a pair of entities, full stop, independent of any specific context. We're trying to determine the relation between this entity and that's it. The other question I want to look at is, what's the output of the prediction problem? Are we trying to assign a pair of entities to a single relation? That's called multi-class classification. Or are we trying to assign a pair of entities to multiple relations? That's called multi-label classification, and it's a different beast. So over the next couple of slides, I want to explore the consequences of these choices. The difference between these two ways of thinking about the input becomes really important when we talk about how we're going to join the corpus and the KB. In order to leverage the distance supervision paradigm, we need to connect those two. We need to connect information in the corpus with information in the KB. And there's two different possibilities depending on how we formulate the prediction problem, depending on how we define the input to the problem. If our problem is to classify a pair of entity mentions in a specific example in the corpus, in a specific sentence, then we can use the KB to provide the label. And this is what it looks like. We have a corpus example like this. We're trying to label this specific example. And to do it, we can check to see if these two entities are related in the KB. Yep, they are. And we can use that to generate a label for this example. Labeling specific examples is how the fully supervised paradigm works. So it's an obvious way to think about leveraging distance supervision as well. It can be made to work, but it's not actually the preferred approach. If we do it this way, we'll be doing things exactly as they're done in the supervised paradigm. It does work, but it's not the best way to take advantage of the opportunity that distance supervision creates. There's another way of doing things, and the other way is where instead we define our problem as classifying a pair of entities, not entity mentions in a specific sentence, but just entities, Elon Musk and Tesla, period, apart from any sentence. And if that's how we define the input to our problem, then we can use the corpus to provide a feature representation that will be the input to the prediction. So if we have an entity pair like Elon Musk and SpaceX that we're considering adding to a relation in the KB, we can find all sentences in the corpus containing this pair of entities, and then we can use all of those sentences to generate a feature representation for this pair. So in this example, I'm imagining, it doesn't have to be this way, but I'm imagining that we're using a simple bag of words feature representation. The bag of words has come from the middle, that is the phrase between the two entity mentions, the blue phrases here. And all I've done is counted up the words in all of these blue phrases across all of the examples in the corpus where these two entities co-occur. And yeah, well, you can see here in the token counts that they include tokens from the various examples. All of these examples together are used to generate a single feature representation This is a feature representation for this pair, and it's this feature representation that my learned model will use to make a prediction about this pair. So this is a very interesting way of reversing things. Instead of using the KB to generate a label to make a prediction about a specific pair of entity mentions in a specific sentence, I'm turning things around. I'm using the corpus to generate a feature representation that I will use to make a prediction about an entity pair in abstraction, an entity pair considered just as a pair of entities. Just one more thought on this. This is still kind of about the topic of joining the corpus and the KB. We've created a dataset class which does that, which combines a corpus and a KB, just kind of staples them together and provides a variety of convenience methods for the dataset. And one of those convenience methods is this one, count examples, which shows for each relation how many examples we have in the corpus, how many triples we have in the KB, and the ratio. So the total number of examples, the average number of examples per triple. For most relations, the total number of examples is fairly large. So we can be optimistic about learning which linguistic patterns express a given relation. I mean, even the smallest one has at least 1,500 examples. That's not really, industrial grade data, but it's certainly enough for the kind of exploration that we're doing here. However, for individual entity pairs, the number of examples is often quite low. So some of these relations are between, some of these ratios are between 1 and 2. Of course, more data would be better, much better, but more data could quickly become unwieldy to work with in a notebook like this, especially if you're running on an ordinary laptop. And this data is going to be enough to allow us to have a fruitful investigation. First, I want to talk about negative examples. So by joining the corpus to the KB, we can get lots of positive examples for each relation, but we can't train a classifier on positive examples alone. We're also going to need some negative examples, or negative instances. So that is entity pairs that don't belong to any relation. We can find such pairs by searching the corpus for examples which contain 2 entities which don't belong to any relation in the KB. So we wrote some code to do this, and there are a method on the dataset class called find unrelated pairs. And when we run it, wow, it found almost 250,000 unrelated pairs. So 250,000 negative instances for our prediction problem. And that's way more than the number of positive instances. If you remember, the KB has 46,000 triples. Each of those is basically a positive instance. It's something that we know is definitely a positive example of the relation. Here we have 250,000 negative examples. It's so many more that when we train models, we'll wind up downsampling the negative instances substantially so that we have a somewhat more balanced distribution. A reminder, though, some of these supposedly negative instances may be false negatives. They may be entity pairs that don't appear to be related, but in the real world actually are. Our KB is not complete. A pair of entities might be related in real life, even if they don't appear together in a KB. And as I said earlier, after all, that's the whole point. That's the whole reason we're doing relation extraction, is to find things that are true in real life and true according to some text that somebody wrote, but aren't yet in our KB. Okay, now I'm going to come to the question that was asked about pairs that belong to multiple relations. And this is related to the question of the outputs of our prediction problem. We wrote some code to check the KB for entity pairs that belong to more than one relation. So that's this method, count relation combinations. And it turns out this is a really common phenomenon in the KB. There are lots of pairs that belong to multiple relations. For example, I won't even mention the most common one, but there are 143 people in the KB whose place of birth is the same as their place of death. And actually, that's not that surprising, right? That makes perfect sense. It even turns out that there's no fewer than 7 people who married a sibling. Well, since lots of entity pairs belong to more than one relation, we probably don't want to be forced to predict a single relation. So this suggests formulating our problem as multi-label classification. We want our models to be able to predict multiple relations for any given entity pair. There are a number of ways to approach multi-label classification, but the most obvious is the binary relevance method, which just factors multi-label classification over n labels into n independent binary classification problems, one for each label. So if you have a pair like Pericles and Athens, you want to be able to predict any combination of these labels. You just train a separate model, a separate binary classifier for each of the labels independently. Each of them generates a prediction independently. And in this example, we've predicted that the place of birth relation applies, the place of death relation applies, but not the has-sibling relation. A disadvantage of this approach is that it fails to, because it treats the binary classification problems as independent, it fails to exploit correlations between labels. For example, there may well be a correlation between the place of birth label and the place of death label. And if you already have evidence that the place of birth label applies, that might tilt you at least a little bit toward saying yes for place of death. This approach of factoring them into independent binary classification problems is not able to take advantage of that information. But it has the great virtue of simplicity. It's incredibly straightforward, incredibly easy to think about and to implement, and it'll suffice for our purposes. It's going to make the investigation move forward very smoothly. So I want to sum up a little bit. We set out to establish a precise formulation of our prediction problem. And when we put all the pieces together, here's the problem formulation we've arrived at. The input to the prediction will be an entity pair and a candidate relation. The output will be a Boolean indicating whether the entity pair belongs to the relation. Since a KB triple is precisely a relation and a pair of entities, we could say equivalently that our prediction problem amounts to binary classification of KB triples. Given a candidate KB triple like worked at Elon Musk SpaceX, do we predict that it's valid? This is really nice because it's a very simple way of thinking about what problem we're taking on. We have a bunch of positive examples which come from our KB. We have a bunch of negative examples which we synthesize from the corpus using pairs which co-occur in the corpus but don't occur in the KB. Now we have lots of data consisting of candidate KB triples, including positive examples and negative examples. We can use that data both for training and for evaluation. And once we've trained a model to do this binary classification, we can now consider novel KB triples, which don't appear anywhere in our data, and ask whether the model will predict them to be true. And by doing that, we may discover new relations that are not currently part of the KB that could be candidates for adding.